This season, this semester, we prepared again another exciting set of presentations as part of the Kent seminars. What's going to be different in this semester than the previous one is that we have several TRB presentations. These are the works that are originated from the ICT projects. And then we have 4 sessions of TRB presentations. First of those presentations will be today. And then you will be hearing 2 presentations today. Those are the presentations made at the TRB, and these are the papers originated from 2 different ICT studies. And the first presentation will be made by Professor Abdulreza Usuli from Southern Illinois University, Edwardsville, and he was also a PhD student at UIUC. He finished his PhD, and he worked with Professor Hashash in the geotech department. And his presentation will be about the effect of plasticity index and dust ratio, moisture density, and strength characteristics of aggregate. Second presentations will be given by Hassan Kazme, one of your colleagues in here, and then in his project with the Professor Tutumla, he's a PhD candidate. We'll be talking about pavement working platforms. These are now some of the results that they got from the test sections out there in here last year. So let's give a warm round of applause for Abdulreza, and then let's start.
Thank you. Okay. Well, thanks for everyone to come here. I wanted to thank the ICT for providing this opportunity. Before my presentation starts, I wanted to ask how many minutes do I have until when?
Yeah, these are, again, maybe I should have made that announcements, TRB style, because we are fitting 2 presentations in one Kent seminar slot. So 20 minutes, 15 minutes, and then we'll have 5 minutes for questions. I mean, if you can keep your presentations with 15 minutes and 5 minutes question and answer, that'll be perfect.
I'll try. Yeah. Before starting, I wanted to get to know you guys. How many of you are students here? And how many of you are students of Dr. Al-Ghadi? And how many are students of Dr. Errol Tutumler? Okay, so my topic here is related to aggregates, and I think that you can get from the slide. And this project was defined by myself and Dr. Tutumler and the TRP chair, Sheila Bashir, couldn't be here. But I wanted to acknowledge my co-authors or presenters at the TRB, Sajjad Salam, my student, myself, Errol Tutumrel, Shira Bashir, and Persila Gama, who was the undergraduate in this project. So I don't want to tell you the general stuff. You know that the aggregates are important. So I'm going to skip this. One of the properties that probably are mostly affecting the strength of the aggregates when they are used in the base and sub-base is the gradation. Then there are some which one is the laser here? The middle one. Okay, gotcha. So in terms of gradation, maximum particle size is important, but this minus number 200C, dust ratio, and plasticity index are also important. And I'm putting here the definition of a dust ratio here, person passing number 200 per person passing number 40. The reason being is that the suppliers that they produce aggregates, they send the aggregates to the job sites, and they are getting paid by weight, okay? So as a byproduct of their crushing, there are going to be some little fine particles inside those. So what they want to get rid of those and get paid for it. What IRAD wants, they want to limit those fine contents because it's going to have a deterioration on the strength of the sub-base and base of the pavement. So in this project, we are going to examine the crushed stone and crushed gravel as the base of the aggregates. And one of the other things that it's important is this angularity of the grain particles, and also definitely moisture content and compaction level. So I skipped past those slides to get to here. In terms of the parameters that different states use to do the quality control on the aggregates. Each state uses its own, basically. And there is an AASHTO standard here that they have a specific, basically specification, and then ASTM. As you see, for the person passing number 200, AASHTO and ASTM says maximum allowed is 15 and 20%. The DOS ratio should be less than 0.6 in one of them. The other one says 0.66. And then plasticity index, again, differences here, 4 versus 6, and then liquid limit 25 and 25. Now, we did some literature search from the specs of the different DOTs and find out that the other states not necessarily following these, and they come up with their own, basically, specification. And in particular, Illinois has this kind of a requirement, saying that the DOS ratio, this minus 200 sieve is a maximum 13% allowed, and this varies from 4 to 9 in terms of plasticity index, nothing on the liquid limit and DOS ratio, except that if the DOS ratio is less than 6, you don't have to do the PI check. If it is greater than 0.6, you have to. Now, the objective of this project came out of that table, saying, okay, what are the effect of following factors on the strength of aggregates? The second thing is that should IDOT go and revise their specs to be compatible with the findings of these study or not? So with that, we developed a kind of like a test matrix plan which has basically a few materials. This is one of them that I'm presenting today. We are going phase by phase. So the first one is a crushed limestone, and we picked the most common aggregate gradation that they use, and that's a CA6 for base and sub-base. Most often that's what they use, and you guys probably have known though that CA6. But in terms of minus number 200 sieve, they accept as low as 5% up to 12, 13%. So we put the three ranges of 5, 8, and 12% to study all of these three percentages. And then in terms of plasticity index, IDOT accepts from 4 to 9%, depending on what is the application, what is the source of the aggregate, etc. So for covering that range, we thought that maybe better to use one with 5%, one with 9%, and then remember the AASHTO by NSTM was saying 4 and 6. So we wanted to kind of cover probably the whole range of these different resources. And then the DOS ratio, there are some standards that they are saying 0.6, and there are some that they don't have any. So we wanted to kind of cover the 0.6 definitely to see what the 0.6 would affect. And then we wanted to see if this exceeds that 0.6, what would happen. And that we used DOS ratio 1. And by doing that, then we had a group basically of samples that are B, C, E, F, and then repeated B, C, E, F for different minus number 200 C percentages. So for these B's, for example, I can show you the gradations that we come up with for example, B 5% and E 5%. It's going to be one type of gradation. And all of them are going to be different when we talk about number 40 divided by number 200. That's the DOS ratio that we are changing. The larger size particles on this gradation are going to be the same for all of them. But all of these are basically labeled as CA6 because they fit the CA6 criteria. So all of them can potentially be sold by the supplier as a CA6 material. That's what we did. And then we brought the materials. Of course, we tried to first sieve them, wash them, make them in separate beans, and then combine those to create these samples for different specification. Now, in terms of the minus, for the plasticity index, I wanted to tell you that the DOS ratio, when the DOS ratio is 1, that means that 100% of passing number 40 is actually equal to passing number 200. So there is nothing between number 40 and number 200 in that sample. It's 0. When it is 0.6, that combination is about 60% in passing number 200 sieve and 40% in between the 200 and 40. So keep that in mind. And then for creating different plasticities for 5 and 9%, the CA6 that we got, the fines had about 11%. Fines meaning the ones that are basically less than 200. And then we had to mix this with other basically fine materials to create exactly that target of 5 and 9. The other materials that we used was different resources from red clay to mineral filler, and then some local soils at our campus. And then by using various combination of these, we identified basically the best combination that provides the target of PI of 5% and 9%. Then after that, we created the samples and we put them together, and first we had to do the compaction curves. We find out what is the maximum dry density and what is the optimum moisture content for each of the samples. So for each of the letters that you see, there is a 5% minus 200, 8%, 12%, the same for E and C and F. For the C and F, you see that those are the DOS ratio of 1. For the B and E, you see that those are the DOS ratio of 0.6. And as you can see out of this figure, these ones typically had higher optimum moisture content, lower dry unit weight, and these ones had higher dry unit weight and lower optimum moisture content. So then we took actually each of these samples that we created here with the to do the compaction. We took all of those, put it under water, and we did the CBR, soap CBR on them for each of those samples. And that would give us the CBR for all the moisture contents that you see on these curves. The standard, actually standard says 4 days, but really we think that that's too long for aggregates. It doesn't need to be 4 days there. It doesn't make any that much of a difference if it is 1 day or 4 days. But anyway, we did it 4 days, and then we got, for example, for this B sample that you see here, B5, that we have 4 points or 5 points of moisture content. Then we extracted 4 or 5 points of the soak CBR for that particular sample. And then the same thing for E5. As you see, the B is going to be the PI of 5 and the DOS ratio of 0.6. This one is the same DOS ratio but PI of 9. Then we did the 8% comparison with all these CBRs. As you see, most of these CBR curves show a peak, and then most of them peak was at the optimum, but not for all of the samples. Like the ones that had the DOS ratio of 0.6 and a PI of 9, we saw that the peak of the CBR doesn't match with the peak of the dry unit weight. And then the other important point that we found out is that some of the samples, in terms of moisture content, they are not very sensitive. When we differ the moisture content, the CBR is kind of like stable, doesn't have that much of, doesn't get influenced that much by variation of moisture content. For some samples, we saw that, no, that's severe. If, for example, the contractor says go and compact this at the site with plus or minus 2% moisture content, then you look at this figure, for example, and say, okay, the maximum is here, but then 2% above that is going to be here. So you are basically coming from this peak to very low value, as you see here, or the same way on the other side. For the loss ratio of 1, we saw more differences between the same minus number 200s. For example, in this case, C and F with the 5% minus 200, there is a bigger difference between the peak values. We didn't see that with the loss ratio of 0.6. The same thing we saw for the 8% and the same thing we saw for the 12%. That when for the samples that have a loss ratio of 1, when the plasticity increases, then the strength is significantly reduced in terms of peak basically strength of CBR and also at various levels of moisture content. So that's basically what it's saying here. And then for in terms of the changes in the put the plots in the same way, but in this time we put it on the PI of 5% and looking at the loss ratio of 0.6 and 1, how would they behave? And that basically is seen that they are kind of like not following the same moisture content optimum, and we saw that from the density curves that they are not having the same optimum moisture content. And the same thing happens here. Not any significant change in peak strength except for 8% minus number 200C. And then we also see that generally the effect of loss ratio on strength is negligible if the PI is as low as 5%. So that tells that really if we control the PI, we don't need to care that much about the loss ratio. If the PI is less than 6, then there is no need to put that loss ratio criteria there. That's one thing. The other thing is that not necessarily the loss ratio of greater than 0.6 would qualify the sample to be bad or very low strength. So a combination of those two can be put in together and eventually find out that what would be the good quality aggregate for the project. This one shows the same thing, but in terms of PI of 9% and then loss ratio of 0.6 and 1. In this case, you see bigger differences between the peak CBRs, and that's what it's saying. The effect of high loss ratio on strength is more pronounced only when the PI is 9%. And then in case of 8% passing number 200C, higher peak soaked CBR was achieved with higher loss ratio. There is something special with this 8% that we don't know yet. We have to run a lot of more samples to find out. When we do the 5% and 12% minus 200C, we see that, okay, it's increasing. But all of a sudden, we see for 8% passing number 200C is kind of like reducing and then goes back. Or vice versa. Sometimes we see that the 5% is giving up the higher strength, and then 12% is giving us low strength. So we expect that the 8 fall in between, but it doesn't. Actually, it goes up and then comes back. And we have found that from the other literatures that it seems that the 8% passing number 200C has a very unique properties. It injects a very unique properties into the sample that we have in terms of aggregates. So that was basically the thing. And then we looked at the variation in this moisture, with the moisture. If this is the peak CBR, then that's not really important because of several reasons. First of all, due to water transfer to the soil, it may be different. The other thing is that at the time of construction, they may not use the optimum. They may use something else. So we wanted to see that what will be the CBR in other moisture contents. For that reason, we came up with a series plots that shows the peak CBR and the CBR at minus 1.5% optimum moisture content and CBR at plus 1.5% moisture content. So for those, we see that for the samples that had minus number 200C about 5%, we saw that they are kind of like steady almost. The middle one for each of these shows the peak one. The left one shows the minus 1.5%, and the right one shows the plus 1.5% of the moisture content. The same thing for C letter, E letter, and F letter. And as we see, the first three of them, the average of those, which is kind of like a very crude estimate of how would these differ with different moisture contents, is almost same. But then you see a little bit drop when you use the PI of 9 and dust ratio of 1. But the good thing is that still this has a 5% minus 200C. But when we go to the 8%, we see that all of these reduced almost in terms of average, and then the volatility is increasing as we go to the 8% because more fines are included. And then when you go to the 12%, you see more volatility in terms of moisture content and the differences between the peak. Of course, with the one that has the highest fine content and the highest PI and highest dust ratio is the one that gives us the lowest basically strength, but across the board we see a lower performance when it goes to the higher fine content. So with those, there are a few conclusions. I'm not going to read through them. We are in this, as I said, in the first kind of like preliminary kind of stages of this, and there are a lot of more tests need to be run to come up with a conclusion that it's solid and covers different, basically, gradations, because right now we just tested the CA6. We're going to go with the CA2, which is a little bit dense graded and with larger particles. Then we have to use different materials, crushed gravel too. This is just the crushed limestone. And with putting all of those together, hopefully we can come up with some specifications for them. Here are acknowledgements, Sheila Bashir, Heather Shop, Del Rabiz, Illinois Department of Transportation, ICT, of course, for the funding, and then technical review panel, and the graduate students and undergraduate students. I'll take any question if you have.
Yeah, we can take a few questions. I think we are doing well with time. Actually, I have small questions. First, is it a 2-year project or is it
Yeah.
Because it's going to be a lot of tests, right?
Of course, it's going to be a lot of tests. Yeah, actually, that's crazy. Yes.
Yeah, and then the other point is that, as you mentioned, that even though we are CA6, the type of the material is so important. Like,
of course.
Limestone or dolomite.
Exactly. You might have this. Yes.
So, in other words, the type of the material that you achieve that
it is.
Oh,
yeah.
Particle shape, of course.
Of course. That's right. There are a lot of factors here that this is kind of like a beginning. I think if you want to go deeper than that, it's endless, because you can take a lot of factors into account and come up with a very sophisticated matrix plan that may take several years to get to that point. And that's absolutely right. Limestone, dolomite. But one of the things that right now is allowed, and that's crushed gravel, and they are very excited to see what would be on the crushed gravel, because crushed gravel in nature has a lower strength than the limestone and dolomite. And exactly, and therefore their strength would be anticipated to be very much different. Right now, there is no distinguish between them in the specification of LIDAR. It says crushed limestone, crushed gravel, all of them treated the same way. Okay, so with that, basically crushed gravel, probably you're going to see more differences than even what we are seeing here.
Thanks. So
Sure.
I have a question. At the end, what you will propose to IDA is just one number, something like that. If it is 5%, don't care about the dust ratio, or it is about
something like that.
Or for the different treatment methods and for the different limestone, or I don't know.
Oh, yes.
Aggregate types, are you coming with a different number, or
yes.
you're just coming one number for all kind of the
Well, we don't know yet until we get all of the results, right? If we see that the crushed gravel, let's say, is behaving completely different than the crushed limestone, which we assume that does, then definitely the recipe would be that, okay, for crushed gravel, you're going to use this kind of control criteria. For crushed limestone, you would use this type of control criteria. However, in terms of different type of aggregates, in terms of dolomite versus limestone or slag or something like that, we cannot do that because we haven't tested those. So we're just gonna go with the ones that we have tested and say these are what we have found, and then if you want to assume that the dolomite and limestone would behave the same way, do it yourself. If not, there need to be a study on the differences of those.
Asha and ASTM didn't discuss this, did it?
No. The AASHTO and ASTM, basically they're putting very top criteria like that, and actually, as you saw, California in that table just don't follow any of those. They if you saw, it was blank in all the control criteria for California, which uses the most of the aggregates than any other state. Texas the same way. They don't. And there are some states that they pick some of the criteria like the PI and maybe dust ratio, but they ignore the liquid limit and the other ones. So that's a good question, but we don't know the answer yet.
Any other questions? If not, let's thank Abdul Reza one more time.
Sure, thank you.
So, it's your turn. You don't have any questions, Jester, right?
I can wait. Doesn't make it's up to you. Yeah, I can wait. Because I wanted to talk to one. Actually, I wanted to go to the lab.
Hello, everybody. We'll be talking about pavement walking platforms constructed with large size unconventional aggregates. At the start of the presentation, I'd like to acknowledge my co-authors, Professor Errol Tutumler and Sheila Bashir. She's the TRP chair. So this paper actually summarizes some of the findings from ICT R27-124 project. The project was based on how can we evaluate the aggregate subgrade materials, which are large size primary crusher type virgin aggregates or recycled concrete aggregates, also large size, or reclaimed asphalt pavement materials, or a combination of both of these two materials, like a blend of recycled concrete aggregates and the reclaimed asphalt pavement materials. So this project had three different objectives. The first one was develop characterization techniques in terms of source, composition, and particle size and shape characteristics. Obviously, we used the enhanced UFI aggregate image analyzer as well as field imaging technique to characterize the shape properties. This work was done by Dr. Moaveni. And then we also ran some large-scale triaxial shear strength tests on these types of materials. But we will not cover those discussion in this presentation. We'll just stick to the aggregate shape characterization. The second one was evaluate field performance. So for this, we actually constructed 12 different construction platform sections and tested it with Atlas for rotting performance. We also did build 12 different asphalt surface low volume pavements and tested with Atlas for rotting performance, and then give IDOT some idea about how to revise and develop their current material specifications and also evaluate the adequacy of current design framework. The current design frameworks only considers contributions of virgin aggregates. They don't consider what type of consequences will have when we are using recycled concrete aggregates or reclaimed asphalt pavement materials. So evaluate the adequacy of current design framework. So this is the graph that shows the current IDOT subgrade stability requirements. For example, what type of aggregate cover thickness you will choose when you have very weak strength subgrade like CBR1 or CBR3. For example, the current design framework says that for CBR1 subgrade, use 24 inches of aggregates. Okay, so this is done for improved subgrade applications, and note that this is not a pavement layer. This is just a working platforms on top of which you place the aggregate base course, and then you build your flexible pavement or the concrete Portland cement concrete pavements. So the typical gradations that we use for this type of application is the CA2 and CA6. CA6 is the material that has 4 to 12% of fines. On the other hand, CA2 is pretty much similar to the CA6 gradation, just with a larger top size. And very recently, IDOT had introduced 3 new gradations, CS01, CS02, and RR01, to adopt more recycled materials, more large size materials in the design of those construction platforms. So our intention in this project is to evaluate these performance of these gradations. So for that, we selected 6 different materials, type A through F. Type A was the railway ballast type riprap size aggregates. Type B was the large size crushed concrete aggregates, and type C was the primary crusher, and those were the largest size aggregates, approximately 6 to 8 inches top size. Then we had type D, 60-40 blend of recycled concrete and reclaimed asphalt pavement materials. Then type E, we had coarse fractionated wrap. By coarse fractionated wrap, we mean that it has very small amount of fines, even less than 1% of fines. And then type F, that's the CA2 gradation, large top size base course aggregate. And type G was used as a capping material. Type G and type E was used as a capping material, and type A and F was aggregate subgrade materials. The reason we are using type E and G as capping materials is that those large aggregates, if you're using out there in the field, if you use those large aggregates, they tend to have large voids in their aggregate matrix. So the idea of using the capping materials is to lock in some of the voids from the top. So these are the pictures that you can see. Type A is the railway ballast size. Then on the right side, you can see the type B recycled concrete aggregates. You can see that CS02, those are very large size. And then you have the type D aggregates. Type E is the reclaimed asphalt pavement. You can see by the color, black color. And type G is the typical Illinois crushed aggregates. Those were from dolomite sources. And type F is the CaO2 material. For the aggregate shape characterizations, why is it important? Because if you don't have enough aggregate shape properties, like if you don't have enough texture, enough surface texture, if you don't have enough angularity, you are not going to get the benefit, the aggregate interlocking benefit that you are expecting from the aggregate base course that will support the load during the compaction phase, during the construction phase. So that's why aggregate shape properties are important. So for aggregate sizes smaller than 3 inches, we use this aggregate image analyzer that was developed by Professor Errol Tutumler. But what about the aggregate sizes above 3 inches? How do you characterize those? For that, we have implemented a new type of field imaging techniques. For that, we used to place these large rocks along with the calibration ball on top of a blue tarp, and we take a picture from a specific location and with a certain resolution. And then we converted the image through binary detection and extraction phase. So with that binary detection and extraction, we were extracting the angularity and surface texture properties. And from that process, we have got these results that you can see on the top right corner. You can see the angularity index. On the bottom left corner, you can see the surface texture index, and on the top bottom right corner, you can see the flat and elongated ratio. From these figures, there are two key takeaways. Angularity and surface texture increased when the crushing process moved from primary to tertiary stage, and then you can also see the black dots tend to have smaller quantities, smaller magnitudes than the white dots. That means recycled aggregates have lower angularity and lower surface texture. Now about the field construction of the test cells. We had 3 different cells, cell 1 through cell 3. Each of the cell had 2 different aggregate subgrade materials, and each of the aggregate subgrade materials had 2 different capping aggregates. One was type G, that was a crushed dolomite, and another one was the type E, reclaimed asphalt pavement aggregates. So we had 12 different pavement working platform combinations, and you can see the longitudinal cross section of these sections. Type A through D, those were the large rocks, and the idea was to, if we can stabilize soft subgrade condition with those large rocks. So that's why we use these large rocks on top of CBR1 subgrade, and regular size aggregates like type E and type F we used on top of CBR3 subgrade. On top of CBR1 subgrade, as I told you, that the requirement is 24 inches of aggregate cover. So for 24 inches of aggregate cover, we placed approximately 21 inches or 53.3 centimeter of large rocks, and then capped with 3 inches of capping materials. And we have alternating capping layers. The odd numbered sections had dolomite, crushed dolomite capping layers, and the even numbered sections like 2, 4, 6, those are the sections had the reclaimed asphalt pavement capping materials. So at the very initial step of the construction, we engineered the soil to match certain subgrade strength. For that, we first established the compaction characteristics in the lab, and we know for CBR1 what is the corresponding moisture content. So we went out in the field, and then we tilled the soil, and we collected the loose soil samples, and with microwave we determined the moisture content. And then we plotted those moisture contents along to specific locations in a cell and see what are the zones that are deficient of the required moisture content to reach the CBR1 subgrades. So through this trial and error process, through this moisture content determination as well as the dynamic cone penetration testing, we tried to achieve a CBR1 condition uniformly all over the field. By CBR1 condition, we are meaning this actually. Virtually, we could not place any of the compaction equipment on top of this soil. This was so horrible. I mean, we were just bogged down. So the idea was to use this excavator bucket and kind of apply thumping motion to just to compact the soil from the top. Once we have done that, we have sealed that soil with an asphalt coating, asphalt cement coating, so that there is no further moisture escape. Then we placed those large rocks and compacted those large rocks in 2 lifts, and the regular size aggregates were compacted in 1 lift since they had smaller thicknesses. Then on top of that aggregate subgrade layer, before placing the capping layer, we had also placed some of the aluminum foils at several locations so that we can track the subsurface rotting performance with ground penetrating radar. For the construction quality control, we use nuclear density gauge, lightweight deflectometer, and aluminum foil lightweight deflectometer and soil stiffness gauge. And these are the compaction characteristics. On the top left corner, you can see the laboratory established compaction characteristics, and the three other graphs basically shows you the compaction densities achieved in the field. The numbers look confusing over here, but just two key takeaways from these graphs is that wrap capping layers achieved comparatively better relative density. That's because in the field we saw that the moisture content of the stockpile aggregates was closer to the optimum moisture content of wrap in comparison to dolomite. So that's why, because of the moisture content being in close proximity to the optimum moisture content of wrap capping layers exhibited better relative density. Similar observation was made when we did the composite surface modulus characterization with LWD and GeoGauge. Wrap cap sections consistently exhibited higher modulus. If you look at on the top left corner, you can see those two sections, type G and type E, and you can see the LWD and GeoGauge measurements. And if you compare these alternative capping layer performance in terms of the numbers that we got for composite surface modulus, type E wrap cap sections consistently exhibited higher modulus. But when we tested it with accelerated pavement testing, we see completely opposite picture. Despite having higher relative density, despite having higher modulus values, exhibiting higher modulus values, these wrap cap sections have consistently showed higher permanent deformation potential, higher rutting potential than the other types of aggregates. Also, another thing was that you can notice from this graph is the top two graphs are basically showing the large rock performance, and the bottom two graphs is basically showing you the regular size aggregates. By comparing these two numbers, you can see that large rock sections survived at least 4,000 passes. Only one section was kind of showed early failure. That was the section 2, which had a very shallow water table, and because of the presence of that shallow water table, that section failed prematurely. For the pavement forensics, we used the geoendoscopic imaging along with panda penetration testing. Panda penetration testing is very similar to dynamic cone penetration, but it is kind of, instead of looking through your eyes, you are actually recording the numbers with a more modern equipment. And after the panda penetration testing, through that same borehole, we installed a geoendoscopic camera, very small geoendoscopic camera, to see what is the depth of the layer interface, what is the depth of the water table. Those information we got from the pavement forensics analysis. Also, to monitor the subsurface rutting performance, we used ground penetrating radar, but this was not pretty much helpful because of the shallow water table that we have seen in the CBR1 subgrade. And the next few slides shows some of the failure patterns. For example, section 2, you can see the section 2 failure pattern, where you can see that rutting occurred both in the subgrade as well as in the granular materials. And this is the section 2 penetration based strength indices. On the solid black line that you can see over here is actually the cone resistance from variable energy panda penetration testing, and the dotted line, the dotted ash colored line, is actually showing you the California bearing ratio. And you can see that beneath that water table, beneath that shallow water table, the strength indices decreased significantly. Then in the section 5, there was very minimal amount of rutting. It's just basically the consolidation of the aggregates, the large aggregates that we have seen in this section. Subgrade strengthened substantially owing to the large rock penetration. compared to this RRO1 aggregates that you have seen in the previous slides for section 2, this one consistently exhibited higher cone resistance, higher California bearing ratio. As you have seen in the last presentation, that with higher aggregate sizes, you experience higher cone resistance or higher strength indices. So that was the case in this section as well. Deeper water table. Compared to the previous sections that I showed you, section 2, this had a deeper water table. The previous section had 16 inches of the water table at a depth of 16 inches. This one had at a depth of 22 inches. So that made a significant difference in terms of the performance. Deeper water table proved to be beneficial for increased subgrade strength. So drainage is quite important. DCP recorded CBR value indicated a 10-fold increase in subgrade strength. What was the reason? Because during construction, during compaction, we mobilized some of those large rocks into the subgrade. It's kind of, you contaminate the aggregate subgrade and you mix it with the subgrade to increase the strength to some extent. This is the failure pattern that you can see in the wrap capped sections. This is wrap over wrap, and this section actually showed the highest amount of heaving on the sides of the wheel path. That means that the wrap reclaimed asphalt pavement materials failed within its structures. Compared to that failure, the subgrade kind of showed less amount of deformation. So that's another key important things. All of the wrap cap sections failed prematurely compared to their dolomite counterparts, as well as when you use the wrap as aggregate subgrade, it also showed significant amount of heaving on the sides of the wheel path. So regular base course size unbound layer exhibited considerably lower strength indices. If you remember the previous graph, you can see that those sections with large rocks were showing CBR range in the range of 80 to 100, whereas this one is showing 60 to 70 in the aggregate subgrade. And CBR reached target margin of 3% well below the aggregate subgrade. That means there was some construction error. We might have ended up with a thicker aggregate layer. No water table was detected up to a depth of 1 meter. So that's another important thing. Despite having a shallower water table, these large rocks performed better. On the other hand, in this section, we did not see any water table. Despite having no water table, this section failed early at 250 passes. So the conclusions: penetration of large aggregates, mobilization of large aggregate subgrade particles into the weak soil was proven to be effective. Somewhat well graded, like type B and type D, recycled materials outperformed the uniformly graded aggregates like the riprap size or the primary crusher run, which had virtually no small size particles, just uniform sizes. Then conventional size base course aggregate did not improve the weak subgrade strength in comparison to the large rocks. Depth of the water table, aggregate cover thickness, shear strength had significant influences on individual rotting performance of the test sections. And finally, reclaimed asphalt pavement exhibited higher rotting potential in both capping and aggregate subgrade layer compared to the recycled concrete and virgin aggregates. So that pretty much concludes my presentation. Thank you for your patience. Please let me know if you have any questions.
All right. Any questions?
Yeah, I have one here. I'm really interested to see, because you take a picture of these aggregates,
Yes.
to represent their angularity.
Yes.
How many samples it is needed to get a good average for that kind of stone, or I don't know, crushed?
It depends on the size. If you have 6 to 8 inches of large size rocks, I think 40 or 50 is a good number. But if you are going to smaller sizes, then the selection should be much wider. So you should have at least 100 particles in that case.
Any statistical method had been done on this?
No statistical method. We just had some numbers let's see if we can implement this field imaging technique first. So that was the idea.
One question.
Yeah, sure.
First, I like the picture. Send it to Mustafa. It's probably the best natural picture I've ever seen. So natural. It's really nice. You took that picture?
Yes.
It's really nice. Question is, you had some lab data for the modulus of individual materials, and you had some field failure data.
The lab data on capping aggregates only. You cannot do Brazilian modulus tests on those large aggregates. I mean, it's just if you have 6 to 8 inches of size or 3 inches of size, it's hard to do Brazilian modulus tests.
What I was trying to ask is, you see some changes in the performance out there, but how much of that should be contributed to the material itself versus construction variability? Do you have field modulus data from the layers? Have you conducted LWD or LWD?
Yes. That was
that?
Yeah. I have shown the results. I mean, you just gave me a small amount of time, so that's why I didn't go through the details.
Okay.
So this is the performance. This is actually on top of aggregate subgrade, and this is on top of actually capping surface. And we also did LWD with geoform as well as FWD, and we tried to match those points, those geoform deflections, using different types of nonlinear resilient modulus properties. We have already done that, but we did not include those results in this presentation of the paper.
And you had also some difference in the thickness of the layer, right?
Yes, but for the thicker sections, like for type A through type D, just remember the depth of influence of lightweight deflectometer. If you think about the depth of influence of the lightweight deflectometer, it's in between 12 inches to 14 inches. And for these large rock sections, we are putting at least 21 inches of rock. So it's most likely that whatever you are seeing over here, those are representative of those large rocks, rather than influence from the subgrade. There will be some influence of subgrade in these sections, like type E to type F, in section 9 to section 12. Those sections is likely to have some subgrade influence, but not those large rocks.
How about the thickness of the upper layers, the change? Because you had some, I think, inconsistency or this variability in the thickness of the...
Yes.
Was it up to an inch or so in the upper layer, asphalt layer?
Yes, even more than 1 inch we had seen.
So the section that failed earlier, did they have thicker asphalt layers or the thinner?
This is, I'm showing only the construction platform, not the low volume roads. And we were trying to analyze the nonlinear modulus properties using the LWD geosensor deflections. So that work is done, but we haven't discussed it over here.
Are there any other questions? Not, then let's just thank Hassan as well.